afternoon to you or today. And the seminar, the talk will be held in English, but before I have to start with some communication to the Italian people that are attending our seminar, especially for our students. So we will start in English within 1 minute. Ok, buon pomeriggio, è una comunicazione di servizio per i nostri studenti, anche gli studenti che stanno frequentando il corso di laurea magistrale in geofisica. Siete pregati per avere, diciamo così, la firma di aver partecipato a questo seminario, di mandare attraverso la chat la vostra presenza, oppure comunicarlo direttamente a Bernardo Carmina attraverso una posta elettronica, quindi bernardo.carmina@unip.it. Va bene, abbiamo a parte questa breve presentazione e adesso passiamo alla presentazione di Francesca e iniziamo il nostro seminario, che come sapete fa parte delle nostre iniziative del giovedì, i nostri webinar del giovedì. Seguiteci sul canale YouTube e seguiteci ovviamente su Teams, e poi saprete le nostre iniziative delle prossime settimane. Sono già in programma altri seminari che vedrete anche sulla barra che scorre in alto, che Bernardo ha predisposto con questo diciamo look da Sky News 24. Ok, we can start now the talk of Francesca. Ladies and gentlemen, good afternoon, and we'll come back to our Tuesday webinar, the webinar of our department. This talk is part of the Basic Analysis course. It's my course in the Master degree course in Exploration and Applied Geophysics. This is a double degree. That's why we are talking in English now, because some students come out from Italy. And now it's for me a pleasure to introduce Francesca Meneghini, that is part of our department staff. Francesca, probably everyone knows about Francesca, but Francesca graduated in Pisa and then worked as a postdoc student in Santa Cruz University in California, in Ouro Preto University in Brazil, and in Stellenbosch University in South Africa. The researches of Francesca mainly deal on the deformation in a brittle and brittle ductile shear zone, especially in clay-rich faults. And then she studied fluid rock interaction and formation of pseudotachyllites and frictional melts. She worked in Northern Apennine, Alpine Corsica, in the Franciscan Complex in California, in Kodiak Accretionary Complex in Alaska, and then in southern zone of Damara Belt in the western Namibia, and in South Africa in the Saldania Belt. Last year, Francesca participated as member of the ECORD IODP consortium to the International Ocean Drilling Project Expedition number 375, I mean, if I remember correct, in the Ikurangi subduction zone in the offshore of New Zealand. So the aim of this cruise was to investigate the boundary between Australia and Pacific plates in the shallow structural level. So now she is going to start, and the title of his seminar is Unlocking the Secrets of Slow Slip Events, the Role of Lithological and Geometric Heterogeneity and the Subducting Plate. So now I leave the word to Francesca, and we will have time for questions at the end of the webinar. So enjoy the talk, and please do not forget to deactivate your microphone and the video connection. Okay, enjoy again the talk. Please, Francesca, it's your time.
Thanks, Luca, and thanks to everybody who are attending the webinar. Thank you so much for inviting me to contribute with this talk to your course. Okay, I'm gonna... okay, you should be able to see the screen of my computer now. Please let me know if there's something wrong. So as Luca introduced, in 2018, I participated to this IODP expedition number 375, and I sailed on board of the JOIDES Resolution, which is the boat, the big boat that you can see here in the picture. And we spent 58 days at sea offshore the North Island of New Zealand to study the slow sleep events. So first of all, I'm gonna introduce briefly the reason why this expedition was funded and the reason why we sailed and drill the Hikurangi margin in front of the North Island of New Zealand. And then I will show the students, as Luca said, the seminar is mainly intended to show to the students of the basin analysis course how we study active margin and how we integrate geophysical information and core information to unravel the subduction in active margins. So why the expedition? The rationale behind the expedition starts from the consideration that the interface thrust in subduction zone can sleep in a variety of sleep styles. You have steady creep, so a movement along the interface that is typical, that occur at typical rate of plane motion, 1 to 10 centimeter per year. And then you can have coseismic sleep. You just need to consider that nearly all of the magnitude 8 earthquake occur along the seismically active part of the plate interface. And everything in between these two end member sleep style can occur at subduction margin. So you can have after sleep, tremor, low frequency earthquakes, and slow sleep events. What are the slow sleep events? The slow sleep events are movement that involve a transient, a seismic sleep on a fault. It's a movement, a sleep that can last for weeks to months. And it occurs at a rate that is intermediate between the plate boundary displacement rates and the seismic sleep. The slow sleep events are recorded both at the upper and lower transition zone of the seismogenic zone. So you have slow sleep event even either at the up dip limit of the seismogenic zone and at the down dip limit of the seismogenic zone, together with low frequency earthquake and tremors. So they are, and one of the main interesting thing that people realized when we started to study slow sleep events is that the place where you record the slow sleep events, it's also the place that is associated to zone of overpressure of fluid. And you can see this in the scheme that that you can see on the right side of the slide. So here is the up dip limit of the seismogenic zone. Here is the down dip limit of the seismogenic zone, and at both sides, both zones are characterized by high VPVS velocity, which is usually interpreted as a manifestation of fluid overpressure. So this is the first thing that we knew about the slow sleep events. So what we can tell about movement on a fault. The movement on a fault is recorded by deformation along that fault surface. And we know from the outcrops, from what I do mainly, which is the field geology, what we know from outcrop studies is that the movement along a brittle fault can occur in mainly two end member fault styles. So you can have and these two end members correspond to different degree of localization of deformation. So you can have wide delocalized fault zone volumes on especially characterized by heterogeneous brittle ductile deformation, and you can see schematization of a wide delocalized fault zone that I study in the Franciscan complex in the picture 1 here on the left, or you can have faults that are very localized in the formation and are characterized by narrow principal slip zone surrounded by various degree of damage zone. You can see here in figure 2 a schematization of this very localized fault. You have a very narrow centimeter to millimeter scale principal slip zone here surrounded by damage zone of various thickness. And between these two end members, discrete fault plane here on the right and heterogeneous continuous discontinuous shear zone, you can have a wide range of fault style that range in between these two end members. And this is schematized mainly by a paper by Fagereng and Simpson of 2010. So what Fagereng and Simpson realized is that you can relate these two end members of faulting style to the slip behavior. So wide delocalized fault zone with heterogeneous brittle duct deformation are generally thought to accommodate low strain rates. On the contrary, the localized fault with narrow principal slip zone tend to accommodate slip during high shear rate events. So you have the principal slip zone that record multiple events of high strain rate events, contrary to the localized fault example. So as I said before, there's a wide range of fault rocks that fall between these two end members. And these end members are usually time dependent. So you can observe a progression from one member to the other in the same fault with time. Which means that a single fault can be characterized by a transitional frictional stability. So since the slow slip events are interpreted to be a manifestation of this transitional frictional stability, meaning that the same fault rock can move in a variety of slip styles, then we can say that the seismic character of this wide variety of fault style can be modeled in terms of how much heterogeneous your fault surface is. And what Fagereng and Simpson did is to model the amount of competent and incompetent material in your fault zone to relate this incompetent-competent ratio to the seismic character. So if you look at this the scheme on the right, you see that when you have continuous deformation in here, you have a low interaction between the competent bodies. You have a high incompetent-competent ratio, and this can be related to a different seismic character if you have a discontinuous dominant type of fault with a high interaction of competent blocks. So the starting point of understanding slow slip events and how slow slip events can alternate with seismic slip along a fault based on this assumption. In the field, you see different slip behavior. In active fault, you see different seismic slip, different slip behavior. So there must be a way to make a correlation between how a fault look like in the field and how it move, with which way of slip it move. So as we said at the beginning, all the different kind of movements along a plate interface, steady creep, coseismic slip, and everything in between, contribute to accommodate the plate motion, and this is for sure. We know about that. What we don't know is what are the underlying mechanisms that promotes one fault behavior versus another. Is the role of fluid? Is the role of the lower plate that subducts? We don't know. We do not know exactly the relationship between slow slip events and big earthquakes. We don't know if they are a precursor of big earthquakes, if they are a consequence of big earthquakes. We don't know. We don't know unambiguously the deformation process and the geological signature of the different fault slip style. Besides pseudotachylite, we don't know how a seismic slip is recorded in the fault and how a slow slip event is recorded in the fault. The existing hypothesis with which we started the expedition is that to explain this variety of slip modes along the subduction thrust, we can invoke mainly the contrasting material properties that enters the plate interface and that can promote this mixed behavior. Or also you might have that low effective stress, for example, by high fluid pressure, can promote the transitional frictional stability that we need in order to have steady creep, co-seismic slip, after slip, tremors, and slow slip events. So bearing all this in mind, why Expedition 375 drilled New Zealand? We went there because Northern Ikurangi hosts the shallowest well-documented slow slip events on Earth. In New Zealand, for obvious reason, there's a very dense system of GPS, and in New Zealand was the first to record slow slip events because of this dense GPS system. What they see is that slow slip events in Ikurangi occur every 1-2 years, and they develop. They are measured on the surface as producing 1 to 3 centimeters of seaward surface displacement measured along the coastline. And the geodetic study show that the slow slip events occur within 2 kilometers to the trench and potentially develop all the way to the trench. And this was a big thing to know because this means that the material that hosts the slow slip events can be reached by drilling. So let's go a little in detail to see what the Ikurangi subduction looks like. The subduction it runs here. This is the lower plate, and North Island of New Zealand is the upper plate. This is a zoom. You can see the frontal accretion, the frontal thrust here. And along this thrust, you have the Pacific plate that is subducted at the Ikurangi trough at a rate that is variable from 20 millimeters per year to 60 millimeters per year. The Subducting Plateau is a Cretaceous large igneous province that is covered by 1.5 kilometers of sediments and is characterized by a lot of basaltic seamounts that protrude through this sedimentary cover. There's a striking difference between the southern margin and the northern Ikurangi margin. The southern margin has a well-developed accretionary wedge. The northern portion of the margin is dominated by tectonic erosion, seamount subduction, and has a smaller accretionary wedge. So there's a difference also in the sedimentary structure of the lower plate, controlling the shape of the accretionary prism and the amount of tectonic erosion. The sedimentary cover is thicker at the southern margin and is smaller at the northern margin. So this is not surprising when you don't have a lot of sediments, as in the northern side, you have a smaller prism and tectonic erosion that is dominant. If you go to the characteristic of the slow slip events, we also see a difference in the two parts of the margin of the Ikurangi margin. The north Ikurangi margin is characterized by shallow, fast, large, and more frequent slow slip events. The southern margin show deep, slow, and less frequent slow slip events. So the drilling transect was focused on the North Ikurangi margin. So the goal was to to study the large, very shallow and frequent slow slip events of the Nordic Incurarangi margin. Here, as I said, the slow slip events are recorded by GPS measurements, and they are characterized by events that last for days and 2 weeks, and they recur every 1 to 2 years. In this same area, you can see it in the blue star here in the map and here in the seismic profile. This plate interface also hosted 2 tsunami earthquake of magnitude 7 and 7.2 in 1947. And these 2 earthquakes, they generated 8 to 10 meter tsunami along the coast of North Island, which is here. So it's obvious the timely importance to understand what's going on here in this subduction margin. With Expedition 375, as I said, we sailed for 58 days from 8 March to 5 May, and we cored and sampled in 4 different sites. The main goal was to characterize the incoming plate, a shallow plate boundary fold, to characterize the material properties of the upper plate above the slow slip events, and to monitor the deformation, the temperature, and the fluid flow by building a borehole observatory along the active thrust. And the main hypotheses that were behind the expedition were to check if the slow slip event propagate to the trench, if the pore fluid pressure is elevated or is controlling in some way the region of the slow slip events, if these events occur in region of conditional frictional stability, so if they are related to multiple slip behavior, if there is a continuum of duration of magnitude, and if there's a control, a mutual control between the slow slip events and the fluid flows along the fault. So what I'm going to show in the time that last, I will show you how we reconstructed the architecture, the stratigraphy, and the composition of the lower plate entering the plate interface to answer mailing hypothesis 3, which is to check if the slow slip events are in some way related to places where contrasting material properties are entering the subduction zone. Here is a seismic section processes that interpreted by one of the people that was sailing with me, and we are going to focus on these 2 drilling sites, U1520 and U5026. U1520 drilled a section of the lower plate right before the Hikurangi trough, and U1526 drill one of the seamount that is almost going to be involved into subduction. If you zoom in the red box here, you can see that you can see that the seismic profiles show a typical frontal part of an accretionary prism. You can see all the shallow thrust, the frontal thrust that branch off from the basal décollement. So this is the plate interface. And what the group that interpreted this section did is to try to prolongate the plate interface trace outside the accretionary prism to see the possible location of the future thrust zone in the incoming plate. So this blue line, this tiny blue line that you can see here, which separate the basement from the sediments, it's where they think the décollement zone will propagate while the deformation and the subduction continues. In the figure below, you see a zoom on the lower plate that shows how rough is the topography due to the existence of many seamount and topographic high in the lower plate. Another interesting thing that I will show more in detail after is that one thing that you do pretty commonly in oceanographic expedition is to continuously correlate and compare what you get from the seismic and what you get from the sediments and rock that you are drilling. So here you can see that the seismic units that the people, the geophysicists, interpreted here are correlated with the borehole data that we analyzed during the expedition. I'm going to show you this more in detail. So let's start with the input size. This is a site 1520 that was reconstructed from drilling 2 different holes slightly next to each other. So this is the whole stratigraphy that we were able to reconstruct. You can see that there's we defined 6 different lithostratigraphic units that range in time from early Cretaceous to Holocene. And you can also see that there's a change from trench wedge terrigenous clasted gravity deposits to pelagic carbonatic sedimentation down to a very peculiar volcanic clastic unit. And this clear change in sedimentation composition is particularly well seen if you look at the carbonate content that we measured during drilling. And you can see that there's a pretty clear jump in carbonate content when you go, obviously, from terrigenous clastic sediment to carbonate-rich lithologies. So unit 1 is the top of the trench wedge, and so I'm going to show you in briefly, but with some detail, the different lithostratigraphic units, and I'm going to show you a few core pictures that you can see here on the right, just to show to people listening to me that are, as myself, more used to field geology, just to show you the amount of effort that you have to do when you're sailing and you're looking at sediment, uncohesive rocks. Can be frustrating sometimes for a field geologist, but this is it. So this is unit 1. It's a trench wedge facies. It's characterized by turbidity, thin to medium bedded turbidites. With the white dotted lines, you can see the base of each turbiditic event. You can see that the bases are always sharps, and you can recognize the bases easily because of the normal grading that I think it can be easily seen also from these tiny pictures. If we go down, there's unit 2. Unit 2 is also characterized by thin-bedded silty turbidites. Here, the silt versus mud ratio is more closer to 1 compared to unit 1. There's a reduction in thickness and in frequency of quartz interbeds. And what you see here, I highlighted some of this, is that you have the turbidite base is usually characterized by erosional contacts and mud intraclast in the turbiditic event that is on top. This unit 2 was interpreted when during the logging while drilling, and from seismic data, it was interpreted to be an avalanche that characterized the margin, which is called ruatoria avalanche. You can see the ruatoria avalanche here. The interpretation of this avalanche is that it's a gravity deposit that was caused by the subduction of a seamount in this area here. Here you can see a 3D image of the ruatoria slide or avalanche. And as you can see, the tail of the avalanche is channelized through the Ikurangi trough. So the idea from the seismic is that this unit with specific reflectors and specific physical properties, I'm not going to go into that detail, could represent the ruatory avalanche. So when we drilled through this unit 2, we were waiting to recover chaotic deposits, and we didn't recover chaotic deposit. As you can see in the 2 cores, there's a thin-bedded turbidite with no deformation or no destruction of strata. So what we think is that probably this side of the ruatory avalanche was just sliding without an internal destruction, maintaining the internal stratigraphy. So there's no evidence of gravity-driven remobilization of the turbidites or evidences of deformation. Unit 3 is again trench wedge faces, is still characterized by normally graded thin-bedded turbidites. There's a planar lamination in the quartz grain interval of the turbidite. You can see some planar lamination here, and in the basal interval here. You can also see that frequently in this unit, there's ash layers that are interbedded in the turbidites. And this is the first unit where we saw events of mass transport deposit, chaotic deposit, as you can see one here, which is interbedded in the turbidites and is characterized by convoluted mud layers. So these layers with different types of green or gray-green are layers of mud that are convoluted together. There's a soft sediment deformation going on here, which we think is related to the fact that this is a mass transport deposit, which, as you can see here, is perfectly interbedded within the turbidites. Below the trench wedge deposits, we go into the carbonatic sedimentation. And this is the first unit of carbonatic composition that we drilled. We called it Unit 4. It's characterized by marl, by calcareous mudstone, and also show a lot of mass transport deposit interbedded. So here you have 3 typical occurrences of this unit. There's a lot of bioturbation going on in the marls. There's a lot of ash layer interbedded between the marls. And you can also see that there's some convoluted flow-banded intervals here and in the core, in core C on the right of the picture. So with the dotted white lines, I try to contour different layers of marls or calcareous mudstone that are developing flow banding structure. They flow in some way one with another, and they develop these convoluted layers where you also have isolated marl classed between immersed in other marl layers, and you start to see some blocks classed of basalt interbedded between the carbonatic layers. The rest of the core was made in a different hole, because every time you change lithology, you might need to change the way you drill, because the physical properties, the mechanical properties of the rocks that you encounter require different drilling tools. So we had to change the drilling tools and drill another hole. And you have to imagine that this section here is a continuous down deep in a different hole in here. So in hole C, we kept drilling Unit 4. And here again, Unit 4 is a carbonatic unit and is composed not only of marls, but also of calcareous mudstone down to chalk. And especially below in the chalk, we saw a lot of debris flow deposit, mass transport deposit, so gravity-driven deposit interbedded in the carbonatic pelagic sedimentation. And here, just wanting to show the beauty of this debris flow deposit. Beauty, I know it depends on taste, but I found this debris flow very, very nice. So we going down in the section, we progressively go from debris flow deposit or mass transport deposit. They are more similar to the one that I was showing before in the other hole. You have convoluted and flow bending mixing on different marl beds. These all occur in sediments. It's soft sediment mixing and convolution and entrainment of different marl beds. And then if we go deeper, possibly because of a lithification state, the change of the chalks and the calcareous mudstone and the marl, you go into debris flow that show a blocking matrix texture. You can see the blocking matrix texture in this sequence of cores here and also in the one more on the right. So you still see convoluted beds like in here, flow bending structure. You see the blocking matrix. You see this rounded marl, calcareous mudstone clast, which are intermixed together. And when you move from this type to debris flow to the deeper one in the unit, you see that the clast, there's an increase of pebble side clasts that are made of basalt. Here, there's one basalt clast. Here is another basalt clast, or the greenish thing that you see are basalt clast. And if you move down section into the chalk, you see that most of the debris flow gravity-driven deposit are characterized by clast of basalt or volcanic clastic rocks. So while you go deeper, you have basalt clast, these two fine grain clast here. You have volcanic clastic deposit in blocks, basalt clast here again. And as you can see, there's a progressive change from debris flow mainly made of marl and mudstone clast to debris flow dominated by basalt and volcanic clastic material clast. And this happened when you go to the bottom of Unit 4. This is the chalk at the bottom of Unit 4, and this is the boundary between Unit 4 and the last unit of Site 1520. The last unit, Unit 5, is a volcanic clastic facies, which is mainly composed of a conglomerate. You can see three different aspects of the conglomerate here. The clast of the conglomerate is volcanic clastic material or basalt material. And interlayered with this volcanic clastic facies, occasionally you can see marl or clay siltstone. Here is a picture of a marl. So the basal unit, Unit 5, the volcanic clastic facies, is a facies that is dominated by grain flow and debris flow mechanism, feeded by a basaltic-rich high that is probably the Seamount, and I'm going to show you why. Here is a very quickly a zoom in the characteristic of volcanic clastic conglomerate. It's a clast-supported conglomerate. The clasts are tightly packed and bound by pore-filling cement. The pore-filling cement is clear in this image here. All the whitish thing in between the clast is a pore-filling cement that is mainly made by palagonite, zeolite, and calcite. There's a few thin section images here. You see basalt clast that are all cemented by different generation of cement. And you can see here we highlighted palagonite, which is a alteration product of the basalt, zeolite and calcite, which are the main components of this cement. So compared to all the other units that we drill, with the exception of the chalk. This was the strongly lithified, hardest thing to drill. And the input side ends with a very complex units that we called Unit 6 that was drilled only for 200 meters until we reach basalt. Is a highly mixed assemblage of volcanic clastic conglomerate, volcanic clastic siltstone, and blocks of basalt. So it was a very enigmatic unit, and we did not spend a lot of time with this unit, because then we entered into basalt. It was hard to drill, and we just stopped it because we realized that we reached the base of the sedimentary cover of the lower plate. So this was the stratigraphy of 1520 here. Now I'm going briefly, what time is it? Okay, I'm going to show you briefly the stratigraphy of the Seamount. So the drill is this little dark line here. We drill a Guyo type seamount that is called Turanganui Knoll, which is this topographic high here. The important thing to say that I forgot about this seismic line is that if you see here, the shape of the plate interface, it flattens here and it goes down here. And the geophysicists think that here, below the plate interface, there's another seamount that was subducted in Quaternary time. So this situation here could be the future situation when the Turanganui Knoll will be subducted. So in this site 1526, we recognize only two types of units, one biocalcareous facies and one volcaniclastic facies. The biocalcareous facies is a monotonous unit of calcareous mudstone and nanofossil ooze of late Cretaceous to Holocene age. You can see here a couple of thin section, and you can see some fossil here shown in two different polarized light of the same image. The Unit 2, the volcaniclastic facies, is made of conglomerate and coarse sandstone, and both of them are volcaniclastic. In figure A, you can see a sandstone, which is made by grains of basalt, bivalve shells, calcareal bioclast, limestone. Locally, you can see some delicate planar lamination. Lithotype B is a sandstone to granule size conglomerate. Here again, you see fragments of bivalve, the white little things that I'm showing you with the mouse. These are all bivalves. And you see fragments of basalts. Shell under the microscope are partially dissolved. And then when you go down to lithotype, to the deeper lithotype, you have pebble, cobble, boulder size conglomerate made of rounded basalt, shell fragments, and they all lies in a sandy matrix. There's calcite cementation here again, as in the volcaniclastic facies that we drill in the lower place. And there's also a pervasive reddish stain on the core and on the basalt block. So this reddish ferruginous stain and the presence of bivalve suggest that temporarily the Seamount was exposed subaerial, so that or in some way it was in a situation of for bivalve to develop. So in a low marine environment, low depth of water depth, even up to a temporary subaerial exposure that could be probably the reason why you have a ferruginous stain on the basalt blocks. The very end of the core of the hole was this big boulder size of fresh vesicular basalt grain, that the blocks that you can see here in the end of the picture. So this under the microscope was a typical basalt with a vesicular texture, phenocryst, and a matrix. So what we usually did, is to try to correlate what we see at the core scale to what the geophysicists see at the regional scale. So what we do continuously when we are on board is to integrate the core information, the logging while drilling information, and the seismic information. For people that don't know, logging while drilling is a technique that allows you, while you're drilling your hole, you can do a lot of physical properties measurement in the hole. And this is called logging while drilling technique. So usually when you do a drill, you have the seismic profile that guides your drilling. So you expect what you're going to drill because you take a look at the seismic profile. While you drill, you measure physical properties, and then you can have direct access to the physical properties while you're drilling. And then when you're done with drilling, you get your core back on the table, and that's how people like me or the sedimentologists and structural geologists start to work on the ship. So you get your core, and you start describing, measuring, and do all kinds of things. And then the three group of people, physical property specialists, geophysicists, and field geologists, let's say, structural geologists and sedimentologists, then they all sit at a table and they correlate all the data. So here you see what we did. So we tied the core and logging data to the seismic profile. And what you get in the end for the field geology is a sort of geologic section of what you're looking at. And this is what you see. It's now this seismic profile looks more like a geologic section, because each seismic unit, SU1, SU2, SU3, has a correspondence in terms of lithology. So you can see the first login and seismic unit from seismic unit 1 to 5 is the heterogeneous clastic succession of the lower plate that I show you, and then we go seismic unit 7, 6, and 8 is the pelagic carbonatic rich section, and then below this blue line there's a volcanic clastic sediments. And what is the blue line? The blue line is the projection of the plate interface that the geophysicists did on the seismic profile that I showed you before. This blue line runs in a stratigraphic interval that correspond to the boundary between the carbonatic rocks of Unit 4 and the volcanic clastic of Unit 5. So what we think is that the boundary between the volcanic clastic and the pelagic section is the weak boundary that the plate interface, the décollement, will follow when this section will enter the subduction zone. And if you zoom into this part of the lower plate, we can see how the lower plate structure can control the development of the décollement and the plate interface. You can see here that the transition from the pelagic section to the volcanic clastic section is associated by a change in the physical properties. Here, there's just a few of the physical properties measured: the porosity, the P wave velocity, the VP characteristics. And so other than this change in physical properties, you also see that the mixed volcanic clastic assemblage is characterized by highly heterogeneous physical properties, because it's a highly heterogeneous unit in composition, texture, alteration products, and degree of cementation of the conglomerate. So what we can see in summarizing is that with this expedition, we were able to describe an incoming plate that is characterized by a highly heterogeneous assemblage of lithologies. You have turbidited units, calcareous marls, calcareous ooze, chalk, debris flow deposit, MTD deposit, volcanic clastic sands, conglomerate, basalt. As you can probably imagine, each of these lithologies has a widely range of rheological properties, which reflects the fact that we measure widely varying physical properties. And you also have a rough topography that characterizes the incoming plate. You have a basal section of volcanic clastic, which is characterized by heterogeneous grain size, heterogeneous sorting, heterogeneous degree of sedimentation, heterogeneous degree of alteration products in the cement. The plate interface seems to project into the boundary between these volcanic clastic sediments and the carbonate sediments. And what we can see by comparing the two lithologies is that the lithologies of the Seamount is very similar to what we recover at the bottom of the incoming plate, meaning that in both cases we were able to reach the Ikurangi plateau, the lithospheric, the ophiolitic section, the top of the ophiolitic section, so to speak. So these carbonate and volcanic clastic dominated rocks are not very common of subduction zone. I've never seen volcanic clastic like this in the fossil complexes that I work on land, for example. And this volcanic clastic, especially the volcanic clastic section, is not typical of places like Japan or other active margin in the world. So what we did in the end is to reconstruct the architecture of the subducting lower plate by depicting the possible feature of the seamount that we drill and all the other seamount that we don't see because they're buried below the sediments. So we reconstructed a possible rough subducting topography as the one that is shown in this section, and we think that this rough topography contribute to the wide range of lithological assemblages. So we interpret the fans of volcanic clastic deposit as coming as gravity deposit from the topographic high of the seamount. So this volcanic clastic deposit that blanket the flank of the seamount introduce a variety of lithological assemblage that is not typically seen in lower plate that are not characterized by seamount, dense seamount, like in the case of Ikurangi. So if you think of what it could happen when the Turanganui knoll will be subducted, it's possibly a situation like this, which is not very different from what we see in the seismic profile for the seamount that is already being subducted. What you do here is that you introduce into the subduction system a lower plate with different lithological, with heterogeneous lithologic assemblage. And what you do when this lower plate enters the plate interface is that you can have different lithological mixing during the formation across the plate interface. So you have different areas where you have various degree of mixing between these two different lithologies. You can see an example here. You can mix different lithologies in different area in a different way. And this may, the consequence of this might be that you have a patchy and highly variable suite of plane interface rocks, which means in terms of deformation and mechanics that you have a long strike and a cross strike in the plate interface. You have big variation in cohesion, elastic moduli, strength, different way of localizing deformation, and possibly different frictional behavior. And this is nice because another typical characteristic of Ikurangi is that you have coexistence of patchy seismic and aseismic behavior. So a long strike and a cross strike in the Ikurangi, the geodetic and seismological data tells you that you have patches, seismic patches overlapping with seismic patches, overlapping with places where you have slow slip events, and so on. So you may end up with a geometrically irregular fault zone with variable thickness, with variable strain distribution, and comprising a mosaic of diverse lithologies that show markedly different physical properties. And the idea is that this can promote different slip behavior. And this might be the reason why in the single margin you have tsunami, earthquakes, slow slip events, tremors, which overlap in space and in time. And that's here just a few pictures from the 58 days. I'm done. Thank you so much. I hope I this was not too boring and it was into the scope of what Luca asked me to do for the talk. Everybody's sleeping.
Okay. No, I'm not sleeping. I just have problems with my video camera. So, okay. Thanks a lot, and I appreciate that you change a little bit the target of your talks, and I think that my students are happy also. Are happy too. Okay. Now we can start with the questions. You can we can try, you just open your microphone and make the questions. If you have too much question, please use the hand in the Teams, Microsoft Teams device, or you can, if you are following in a YouTube channel, you can use the chat in YouTube channel or even the chat in Teams. So let's go.
I hope it wasn't too complicated for the students, but if you have questions.
No, I don't think so, because we studied this kind of geodynamic system a couple of weeks ago, so should be okay. And I invite my students to make some questions first, but of course, all can do this. Bernardo, puoi guardarmi te la
Sara Guerini ha una domanda.
Sì, guardo io, Luca.
Ok, Sara, puoi aprire il microfono.
Sì, non riesco ad accedere alla chat, non so perché, quindi ho alzato la mano per quello. Faccio la domanda magari in inglese, così un po' tutti possono seguire. Thank you very much for the very nice webinar. My question is, to what extent do you think that the structure you have shown in the last slide related to deformation, shear, fluid rock interaction along the plate interface in subduction can be preserved in an exhumed melange or sedimentary melange in ophiolitic rocks, for example, in the Alps or in the Apennines?
Okay, thanks for the question. Let me, as you saw in the introduction, yes, especially for the people like myself who sail in the expedition, the starting point was actually the field, because what the field tells us, I'm gonna probably share the screen again. So I show this image at the very beginning. At the very beginning of the talk, right?
Yes.
So in what you see in the field is that usually you have situation like this, where you have, let's say, a blocking matrix type of brittle fault, where you have high competent, highly viscous, strong, hard material enclasped, like this light gray things here, which are immersed in a fine-grained matrix that is obviously less competent, more incompetent. It flows in a viscous way, while the big blocks deforms in a brittle way. And this is one possibility, okay? The other possibility, and this is also typical of clay-rich lithologies. When you have a fault that runs into a clay-rich lithologies, this is usually what you end up with. If you have a higher proportion of competent versus incompetent, so when you have a fault that runs into hard, strong material, what you usually have is that you end up with this situation here, where you have a very localized, narrow, principal slip zone surrounded by a zone of damage. Okay. So this one in the scheme, this one is the type 2 fault, and this one is the heterogeneous delocalized fault zone of this image here. So here in the Fageren and Simpson scheme, you have a discrete fault plane here. All the energy, all the movement is accommodating along this discrete fault plane. If you go at the other side, you have a heterogeneous, continuous, discontinuous shear zone. And the meaning of this continuous, discontinuous shear zone is that you have a mixing between competent and incompetent material, and you have highly viscous and lower viscous material, which is mixed together. So you have places, this corresponds to a different distribution of the shear strain. Okay, so if you compare this diagram here with this diagram here, you see that here you have only one peak of shear strain, which is located where the discrete fault plane here is, and here you have different peaks of concentration of shear in the incompetent matrix, separated by places where you don't accommodate shear strain because these are the competent block. Yes. I'm not sure if
it's clear. Yes.
If you go back to the last picture, it's clear that if you mix together mud-rich, clay-rich, terrigenous unit, carbonate-rich units, and volcaniclastic units full of alteration products like zeolite, calcite, you are mixing things that have a completely different rheology and a completely different response to sleep. Okay, clay-rich material is velocity strengthening, let's say. Carbonate has a different seismic characteristic. They shear under completely different conditions.
Yeah.
Some lithologies are more prone to shear in a seismic ways. Some lithologies tend to strengthen together with sleep, so they don't. They're not favorable to produce seismic waves. And you can say this not only looking at the geology, but also looking at the physical properties. And this is why going into an expedition like this is important, because you're continuously working in a multidisciplinary way. I learned so many things from physical properties and geophysics in these months, because you're able to look at the same lithologies from different angles. So going back to the answer, if you mix if you put all this mix of things that you see here into a subduction system, and if you put a topographic high into the subduction system, like it is shown in here, you're introducing in the system a lot of different lithologies. And what happens in the plate interface is that the plate interface, if you look at in detail at the plate interface, you will see something like this. And each color in here is a block of competent rocks from the various lithologic assemblage that you are introducing. And if you keep going down, you keep mixing these different guys together. And if you go along strike in another place where you don't have a subduction of a seamount, you might not have the volcanic clastic deposit, and you might end up mixing only the turbidite deposit.
Yes.
And obviously this, the result of this is that from the seismological and geodetic point of view, what you measure across strike and along strike is a patchy lower plate or a patchy interface with places that tend to move and sleep in a different way.
Yes.
So we're not saying that we discover something particularly revolutionary, but what we're saying here is that probably the fact that the Ikurangi sleep on a different type of sleeping style, it's because the lower plate is characterized by an heterogeneous lithological assemblage of many different things.
Yes. Thank you. Yes, it was perfectly clear. Thank you.
Okay. Thanks.
Okay. Thanks. Some other questions?
Francesca, sono Sergio.
Oh, Sergino, ciao.
Ciao. Non potevo mancare. La dico in inglese se vuoi per gli studenti.
Ok, grazie.
Okay, no, I just want some extra information. It's more about curiosity about the volcanoclastic sequence. So what is this? Is made of basalts and what kind of physical properties have, and what is the contribution in the sleep process?
Okay. The contribution of the sleep process is under study, and so I took sample of the volcaniclastic because I wanted to try to make experiments with the volcaniclastic. So I cannot answer that question yet. I will just show you some more detail. I didn't spend a lot of time because I had to say a lot of things. So let's see if I can do this. This is not very professional, but it's not a very professional way of zooming, but I think it should be clear here. So this is the most common appearance of the volcaniclastic. I don't know if you can see the screen.
We don't see Francesca.
Sorry?
We don't see.
Oh, I didn't
image.
share the screen yet.
You
Okay.
just share the screen.
Yeah, you have to share the screen before. Okay, it's going.
Okay. So I made a zoom, one of the core picture that I show in the presentation. Here you see everything that is brown, lightish green, greenish gray in color is basalt, is highly altered basalt clast. And everything that is white, milky white, is the cement. So it's a conglomerate that deposited as a conglomerate. And then later on, it was cemented during, I think, during diagenesis. So what we think it happened is that, as you saw from the seismic line, we are very close to the Turanganui Seamount. So the idea that we reconstructed also in the last figure is that the flanks of the seamount are the source of this volcanic clastic deposit. So there's landslides or gravity deposit from the flanks of the seamount that produce this amount of basalt clast that are gravity deposited on the lower plate, and then during diagenesis and lithification, they get cemented by the cement. And before that, they get also, there must be a time gap between the sedimentation of the conglomerate and the cementation. And the reason, I think, it's clear on the thin section. The quality of the thin section is not really good, because these are the thin section that were done during the expedition. So you see the basalt blocks. Yep. You see that they are all rounded, sub-rounded in shape. And the reason why most of them are sub-rounded is because each basalt, you can see it's highly altered basalt. All the vesicles of the basalt are filled by palagonite. There's a rim of palagonite bounding all the clast. And then you have zeolite and calcite cement. You can see the zeolite and the calcite clearly in the polarized light. You can see the palagonite in the rims of the basalt blocks, and you can see palagonite into these big vesicles here at the bottom of the figure. So this is the texture of the volcanic clastic. What I did so far on the sample that I collected is that I analyzed the stable. I did a pilot study of stable isotopes on the cement, and it was a very preliminary study. I think I showed it at AGU last year to see if there was a difference. What was the features, the geochemical characteristic of the calcite in the cement, and the plan was also to do grain size distribution across the volcanic clastics, because there seems to be a difference in the grain size and the distribution of the basalt clast in the volcanic clastics, going from the top of the core to the bottom, to down depth. And the other thing that I would like to do is to do a shear experiments on the volcanic clastics, because if we are right that the plane interface will run at the boundary between the volcanic clastic and the carbonatic pelagic rocks, it would be nice to see how this lithologies will shear. I don't know if I answer your questions.
No, okay. I mean, it's interesting. There is a lot of zeolites.
Yeah,
because zeolites are very instable. They can dehydrate under sleeping conditions, so they might contribute for extra fluids as well.
Exactly. So what I was trying to very briefly say here, because the time was running, and probably people are not very familiar with physical property. We are not familiar neither. You are the expert, Sergio. So here I only show porosity, P wave velocity, VP, and the clay mineral content and the calcite content. And you can see that there's the volcanic clastic is very heterogeneous in all of this. In all of these properties, and I think that this variability, as I said in the slide, reflects the fact that you have an heterogeneous texture. The amount of cement is highly variable across the section. The composition of the cement is highly variable. There are places where you have more zeolite, places where you have more calcite. The amount of alteration of palagonite is also varying a lot when you go from the bottom to the top of the unit. So it truly is an interesting unit, because I'm expecting that even in this unit you will find different slip behavior and different rheological mechanical conditions. So
okay.
it's a high heterogeneous unit itself.
Yes, yes. Thank you, Francesca. We can speak later about a few ideas. Thank you.
That was lovely. Thanks.
Okay, Francesca, Edoardo have a question for you. Please, Edoardo, you can switch on your microphone.
Ok, ciao Francesca, mi senti?
Ciao, sì, ok, one Edoardo, Sanità Edoardo. Not Barbero, okay.
just a curiosity. Are there analogies, similarities between the avalanche deposits of your work and the Bocco shale deposits in the internal Liguria units of Northern Apennine?
Allora, probably the position of the if you look strictly at the position of this chaotic deposit, probably the structural position is not the same as the Bocco shale, but for sure I think that the geodynamic meaning of the mass transport deposit is probably the same. It's in this case, it's at least, as you can see, there is a lot of basalt clast in the MTD deposit, especially when you go deeper in the section, like the mass transport deposit reaching basalt that I show can come mainly from this interval here. Is my screen still in a sharing mode? I think so. You can see the section, right, Edoardo?
Yes.
Yes.
Okay. So the Bocco shale mass transport deposit would be in more like here, right?
Mm-hmm.
But that's just because in the Apennines we see the Bocco shale there.
Okay.
What I'm trying to say is that in active margin you could have a situation that allows you to deposit a similar Bocco shale deposit interbedded in turbidites, depending on when you are in the evolution of the system. So the mass transport deposit that is here in the unit 3 trench wedge faces is this figure here. Debris flow, this one.
Okay.
And to my opinion, it's not really different from what Luca Pandolfi showed me when we first showed me some of the MTD chaotic deposits of the Ligurian Apennines. I don't know if you agree, Luca, but the texture is very similar. There's a lot of soft sediment deformation going on in the MTD deposits of the Apennines too. The only difference is that here you're looking at the MTD deposit of yesterday, and the situation in the MTD that you see in the Apennines, or even worse in the Alps, they went through accretion, collision, exhumation. So the story is more complicated, but I totally agree when people say that a lot of the chaotic deposit of the Apennines record a lot of soft sediment story that is completely obliterated, but it's there. And the reason why I say this is because what you see in the actual margin is similar to what we see in these two sets of core images here. What do you think, Luca?
Yeah, I agree, and I like your core too. Yes, I agree. The position is not exactly the same of the Bocco shale, but it doesn't matter. This is what happened in this environment. So yeah, yes, I agree.
The main difference is that the Bocco shale is the last depositional event that we see in the Apennine. But
don't forget that you have the Seamount here.
Exactly.
So it's something different from the
and you also
lithosphere. So
you also have Seamount that were already subducted. So I imagine that the effect of the subduction of this Seamount here will last in time and affect the stability of the front of the system for a long time. So you have a feeding source of chaotic deposits, either from the prism, from the instability of the prism due to the subduction of this guy here, and you have gravity-driven deposit that comes from the lower plate due to the rough topography that you're dealing with.
Okay, thank you, Francesca, very clear.
Thanks.
Okay, students? Okay. Oh. Iole?
Lots of people from different universities.
Iole, you can switch on your microphone and you can.
Hello, Francesca.
Okay.
Hi.
Thanks for the nice talk. This was very, very nice. That unfortunately I was able to follow only already started because teaching engagement before. Therefore, I arrived and I followed at the beginning on YouTube, and after I arrived on Teams. But I arrived just on YouTube at the moment when you were talking about the bottom of Unit 4 and the top of Unit 5, if I well remember, and exactly where you introduced the unit with pebbles and cobbles or boulder of basalt. In a matrix that, if I well understand, is mainly carbonatic or marly.
Yes.
And are the cobbles, the pebbles, only of basalts? And this is controlled mainly, in your opinion, by the basement of this group of sediments, or you have found also ultramafic pebbles and cobbles?
Okay. Let's go back to the sharing. Basso. No. Okay, so this is the base of the lower plate. No, I don't want this. I want the other one. So you're talking about this lithology here, or maybe the very last unit?
Yes, yes. This one. This is Unit 5. Is the top of Unit 5 is correct?
Okay.
Or all the Unit 5 that is made of this. I don't remember.
Okay, allora, Unit 5 is the volcaniclastic phases. So he's, let me go back. Okay. So here there's the contact between the carbonatic pelagic section and the volcaniclastic, right? Okay, let me do this. This is the volcaniclastic phases, and it's all made by the conglomerate that I was explaining to Sergio before. So it's a conglomerate made of clast of basalts, and the conglomerate is cemented by zeolite and calcite. And the base of the lower plate that we drill, which doesn't mean that it's the base of what we think is the base of the sedimentary cover. It's this unit here, unit 6, that was very, very complex and enigmatic, because while we were keeping drilling, we were keeping encountering different lithologies. So here you have unit 5. This is the end of the volcaniclastic of the unit before. And then you have a block of basalt, highly disrupted core material, all made of basalt. Then we were able, drilling this thing was very, very hard, and it took us a long time, because it takes a long when you drill real rocks. This was a layer of siltstone, finely laminated siltstone, which continues here. And then we go back to blocks of volcaniclastic material, which is similar to the one of the volcaniclastic sensu stricto unit. So you have blocks of basalt cemented by zeolite and calcite. Then we encounter pieces of limestone, another piece of siltstone, other blocks of basalt and volcaniclastic material, and then right at the end of the coring, we started to drill solely into basalt. These are all basaltic blocks. You can see the vesicle filled by material. We never, the reason for the blue-black stain that we saw in all this core material is because there's we saw a lot of pyrite in the siltstone material. There was a lot of pyrite in the smear slide and in the thin section, and all this unit measure high values of total organic carbon. So we believe that the stain probably has something to do with this. But the only hard rock material that we drilled is basalt. There's nothing ultramafic, nothing that is below basalt in a ophiolitic section. And it was the same in the Seamount. So we drilled the Seamount only for less than 100 meters. So this little drill site here, it's only 100 meters thick, is this one. And the volcaniclastic, they have this characteristic, the conglomerate has this characteristic typical of being deposited not on the lower plate, at the base of the lower plate, but it was material that was deposited on top of the Seamount. So it was full of bivalve and stuff like that. And the only hard rock of non-sedimentary composition was this boulder-sized cluster of basalt. And we considered this, because drilling this was very time-consuming, we decided that this was the base of the Seamount plateau, and we decided this was the end of our drilling of the Seamount, because we reached the top of the basaltic section of the Seamount. So going back to the volcaniclastic, the fact that we don't see ultramafic clast into the volcaniclastic for us means that this gravity-driven deposit coming from the top of the Seamount were only able to scrape off the shallower section of the Seamount stratigraphy. So this volcaniclastic fan that you can see here in this schematized section, they were probably only fed by the shallow part of the Seamount. Did I answer?
Okay, yes. Therefore, you think that is strictly controlled by the lithostratigraphy of the basement, where the sediments are tectonically eroded, if you want to use this term, or is a control of the basement, and therefore is this possible, do you think, or I don't think that is a selection, because actually high graded ultramafic has the same density of a basalt, or therefore I think that is a problem of composition of the basement.
I'm not sure if I have enough data, and I'm not sure what you mean with basement, but I just think that, well, at least
I suppose it is not easy to understand which is the basement of this association of rocks, because they are.
Sure.
No?
When I say basement, or when I say that we stop drilling, I'm meaning I'm referring mainly to let's say an ophiolite section, right? So we sample and we drill through the typical sedimentary cover of an ophiolite, and then we encounter these volcanic lastics, and then we found basalts, and so we realized we thought we were reaching the top of the ophiolite section of this lower plate.
Okay. Therefore, we can imagine that you found mainly basalts because they are the most abundant clusters and pebbles in a sequence like this one.
Yes.
You cannot exclude that there are very few other pebbles.
Yeah, the only thing I can say is that this gravity-driven deposit were only able to scrape off the upper part of the seamount.
Yeah,
and
okay.
They were not able to sample anything that is below the basalts in the section.
Yeah. Thank you.
Thank you.
Any other questions? Okay, Eduardo, yes. The second Eduardo now.
The other one.
Yeah.
The other one.
Just like the king. Thank you very much for your really nice presentation, Francesca.
Thank you.
It was really interesting. I have a question about the position, the projection of the plate interface. If I understand well, do you think that is mainly controlled by the physical properties of the subducted sediments? But what can be the role of the topography, so the presence of the seamount? And a second question is, how the position of plate interface can change at a great depth? I mean, when a seamount is subducted, do you think that something can change in the parameters, in the thing that control the position of the plate interface?
Okay, I think this image here might be of help. So what Phil Barnes and colleague did. Okay, you can clearly see when they did the interpretation of this seismic line. I didn't put the original one without the interpretation, but I can show it to you. This reflector here, the plate interface, the décollement below the accretionary prism is very well seen in the seismic line. So what they did is to follow this. And they also, what they did also was to recognize the seismic units here in the Ikurangi Trough. So you can see the different lines with different color. These are boundary of seismic units. And based on the feature of this reflector here, they try to correlate the stratigraphy here in the, let's say, in the undeformed section to the stratigraphy here. So you can see that this green line in their interpretation can be correlated to this reflector here, the red line, the green line, and so on. And they did the same with the reflector of the plate interface. And what they realized is that the plate interface runs on top of these two VB HKB basement rocks. Okay.
Okay.
The interpretation here is basically done by projecting this boundary between VB, HKB, and the sediments in the lower plate. But obviously, we do not know. I mean, there are several papers that model the fact that you can decapitate a seamount when you subduct it. So the plate interface can decapitate the seamount, and there's places in the world where you do see this. So I think it's not me that did this, but I think what they wanted to show here is to, let's say, okay, the lithological control on the plate interface is probably represented by the change from this carbonatic terregenous sedimentary sequence down to a volcanic clastic rock. Yes. Obviously, we do not know. I mean, this little guy here could be easily decapitated by the plate interface. We don't know this.
Yeah, probably.
I think the reason why they are doing this, it's also it goes back to this picture here. This picture here, they believe that this bulging of the plate, the shape of the plate interface, is due to a seamount being subducted, which means, to answer your second question, that from the geophysical point of view, they think that you decapitate a little bit, but also the subduction of the seamount impose a change in the shape of the plate interface.
Okay. No, so I think it's really nice.
In the end, I don't know the answer. I mean, I don't know exactly.
Probably it can be a combination of both.
Nobody knows. It might be a competition between these two. Yeah. I'm not, even from a logical point of view, I don't imagine that you simply decapitate without changing your trajectory, right?
Okay, thank you.
And if the internal heterogeneity that I was describing before, that we see in the volcanic clastic, maybe this can also control. Let's say the plate interface could run into the volcanic clastic and follow a specific weak layer into the volcanic clastic instead of following the boundary between the calcareous pelagic deposits and the volcanic clastic itself. It could follow a weaker horizon into the volcanic clastic, and in this way, considering that you have volcanic clastic also tapering the seamount, you could decapitate a little bit of seamount and then running through the seamount because the weaker horizon is there. But either way, you have to change the trajectory of the décollement at depth, which is what you see here clearly.
Yes. No, thank you. I think
this is all speculation, obviously.
It's really nice, and I agree with you about the role of the volcanic clastics and the possible role of volcanic clastics in controlling the plate interface. Thank you.
Thank you.
Okay, Laura.
A curiosity about fracture veins. So, did you find open fracture, filled fracture veins? Did you find a correlation with depth, or more chaotic, or are linked more to lithology? Did you check this correlation?
You mean in the lower plate? Because obviously I didn't show, I'm just talking more for the structural geologists here in the audience. I didn't show anything about the frontal thrust that we drilled, this U15-18 core here. So in the frontal thrust, we saw a lot of field fracture, a lot of oriented field fracture that were, or field faults, minor faults that were related to the main thrust. In none of these cores, we found evidences of veining or fracture or mineralization in veins related to faults and fracture.
And then, but did you find also something then in the footwall that you could compare, or are different structures?
In the footwall of the thrust?
Yeah.
Okay. The U15-18 is it's one of the shallow thrust of the frontal side, and it's a thrust that runs into the pelagic section that I show here in the incoming section. So it basically it juxtaposed this terrigenous clastic turbidite sequence over this one. So there's no comparison with something that could be the plate interface. We have defined the possible plate interface here, just because we drill a very shallow thrust. So we were not, with the JR, we couldn't go this deep, as you know.
Yeah.
So we couldn't, it was out of the goal to go into the plate interface, because we didn't have because the JR cannot go that deep.
No. So you had this flow structure like disturbance that you showed.
Okay. Well, yes, we the good thing about having drilled the lower plate before the thrust is that we already knew that there was a lot of soft sediment deformation going on in the incoming site. And so this situation like this one were already clear that were present as a sedimentary situation of soft sediment deformation before the deformation related to the thrust. So this helped a little bit when we drill the fault. Yeah, this is for the students. One thing that is very, very difficult when you look at this type of core material is that it's very hard to discriminate soft sediment, drilling deformation sensu tectonic deformation, or soft sediment deformation. So when you are in the field, it's hard to, especially when you look at low-grade rocks, it's hard to tell if you're looking at a tectonic deformation or soft sediment deformation. When you are on a ship, you also have the complication of drilling-induced deformation. So what Laura and I were saying is that it's good to, in this expedition, it was good that we drill the lower plate first, because that was the undeformed end member before drilling the fault. So we knew what the starting lithologies look like before the fault. So we were able to discriminate what was a mass transport deposit and what was a tectonic mixing between lithologies.
Okay, the time is almost over. You have two questions. No? The first is from Maria Iole Spalla again. Okay, Iole, if you want.
Yes, very short one. Have you already investigated the composition of the basalt or not?
Not that I know. That's the question. The thing is that, as you probably know, when you take samples on the ship, you have to you only take home the sample that you requested from the beginning. So you present a research project and you say, okay, I'm going to collect basalt because I want to do petrography and geochemistry of that basalt. And I didn't do a sample request for that. There was a team of people. Marta Torres was one of the people involved in this. So there are people that collected the basalt to do petrography, petrology, and geochemistry. And for what I know, there's nothing published yet on that.
Yes, this is what was also my question, Francesca, about the geochemistry of the islanders. Okay, Matteo. Matteo is a student. Please, your question, Matteo.
Good evening, Professor. I have seen in the log data that there are porosity log, gamma ray logs, and sonic logs. I wanted to ask you if you have also other kind of data that are not shown in this talk, and in particular I want to ask you, how did you retrieve the calcite percentage and clay percentage, if you have used a log, a log data, or if you have used, for example, X-rays in lab.
Okay.
And
okay,
I have also seen that in log U1520 you had some not coded sequence portions, and if you can tell me why you couldn't code this kind of sequences.
Okay, so I guess this can be of help. Allora, concerning the carbonate content and the clay content, we measure with both. So the carbonate content was measured while drilling, and also and the clay content was measured also with XRD. So when the core, so there was some measurement, the physical, with the logging while drilling, we measure a lot of other physical properties. I'm not sure I remember all of those, but here we just reported only the main one. You can see ultrasonic caliper, gamma ray, resistivity, VP, velocity, density, porosity. These were all measured in the logging while drilling. And then we also did, when the core was on the table, we also, one of the first things that we measured was to take sample for the carbonate content, and then we took sample for the XRD, and the XRD was running daily during the expedition, so we would get XRD data on the ship already. The problem we have in the specific expedition is that there was some problem that I don't even remember in detail. They were only able to measure the total clay content and not the, let's say, the smectite. We were not able to discriminate between clays. So we only measured the clay content, and then one of the scientists, the guru of XRD data in IODP expedition, which was sailing with us, he took all the samples and he did clay content in specific when we were back home. But the carbonate content was measured in both ways. There was organic and inorganic chemists that would take all the fluids. We used to call them the squeezers, because they would squeeze the core as soon as the core was split in two to take all the water, all the fluids, and analyze the geochemistry of the fluids. So the carbonate content was done in both ways, and most of the clay content was done in XRD during the expedition. The other question was
the not recovered part.
Yeah, for
sorry?
Not
the recovered part.
The not covered portions.
Okay. Not cored means that we made a mess while drilling. So sometimes you drill the core and something wrong happened, and then when you retrieve the core, there's nothing in. There's only water and some mud and some pieces of rocks, and there's nothing. The stratigraphy is destroyed. So that another in the specific not core section here, it was mainly a problem of it was a decision of the core of the chief scientist in some way, where we were looking at very monotonous section we would go through quickly. So we would drill without coring to go faster. Because to drill and core all the section that you see here in the picture, you need weeks. Well, let's say days, because most of these are sediment. But so not core can mean that it was a decision taken by the chief scientist not to drill, or it can be a no recovery area, which means an area where your core was a mess and you throw it away, basically.
Perfect. Thank you very much.
Okay, Francesca. One more question. I mean, the last one, because the party is almost over. We have 2 hours and are almost finished.
Yeah,
so
it's almost year time.
The last question, Eusebio.
Yes, if I can. So I saw that your seismic section were pre-stack time migrated and then depth converted, I suppose, because your vertical scale is depth.
I suppose too. I should probably know better, but I guess so, I trust you.
So the question is, if you have checked, because the seafloor is not flat, but has some different topography, the seafloor. So if you have checked that this has no effect on the deep and depth of the underlying reflectors, because usually pre-stack time migration is work well when you have no lateral variation in velocity. Instead, in this case, looking at the seafloor, it seems that you have some strong lateral velocity variation.
So you're saying that
if I'm right, sorry, excuse me, if I am right, the top of this section represents the seafloor. It's okay?
Yes.
So if you move laterally, there is a strong variation in velocity. Not this slide, the previous one. If you move from left to right, there is a strong variation in velocity because the velocity of water is different from the velocity of the sediments.
Right.
Okay, so this could have an effect on the position of the reflector below below the seafloor, because pre-stack time migration works well when there are no lateral velocity variation. So the question is, if you have checked if this has no effect on the position and deep of the reflectors that you have interpreted below. Maybe this is not important because the deep of the sea floor is not much pronounced due to the scale. However, looking at this picture, it seems that this is quite deep, so this could have an effect on the position and depth of the reflector.
Okay, I think I cannot answer because I don't have enough knowledge of the geophysics side. What I can do, to go back to your question, maybe in a couple of days, I think that all this, for my experience, these are technical aspect of the way that the seismic section was processed, and I think all this is in the proceeding of in the method that the geophysics use to interpret this. So what I should do is to go back to the preliminary report and the IODP report on the expedition and check what you're saying, because at the moment I don't know what to say. I really have no idea.
It could be a suggestion for the next time.
Sure.
Thank you very much.
Okay, Francesca, I think that we can finish because the time is over, and I'd like to thank you again, one more time, and all the people that follow us. And please don't forget to follow the YouTube channel of our department, because we are organizing other talks, other seminars. So follow us and enjoy your afternoon. See you the next time. Ciao a tutti ragazzi e grazie.
Ciao, grazie.